Let's extend what we've learned about probability to look at three topics: odds, expected value, and conditional probability. So first, a quick review of the definition of probability. We said if an experiment has equally likely outcomes, then the probability of event A is the number of elements in event A divided by the number of elements in the sample space. So when we found probability, we were basically doing a lot of counting of things, counting the number of elements in the sample space for our denominator and counting the number of elements that we were interested in for the numerator. So if we had, let's say, a box of 5 marbles, 3 are white, 2 are red, and we wanted to know the probability that we would reach into this box and randomly draw a red marble, the probability is 2/5. There are 5 total elements in the sample space, and 2 of the 5 are red. So let's look at the definition of odds. Now there's two types of odds. There's odds in favor and odds against an event happening. So for the odds in favor of an event, we're going to express that in terms of a ratio, and it's the ratio of the number of favorable outcomes to the number of unfavorable outcomes. The odds against an event A happening would be the number of unfavorable outcomes compared to the number of favorable outcomes. So if we have the same box with 5 marbles, 3 are white, 2 are red, and we want to know the odds in favor of drawing a red marble at random, we would say that drawing a red marble is a favorable outcome, and there are 2 ways to do that. And drawing a white marble is an unfavorable outcome, and there are 3 of those. So the odds in favor of drawing a red marble are 2 to 3. Now you notice that in this case we're expressing the odds using a colon. Odds are a ratio, and there's 3 ways that we can write ratios. We could write something that looks like a fraction, or we could write literally the word 2 in between the 2 things we're comparing, or as you see here, we can use a colon to separate the 2 things we're comparing. The odds against drawing a red marble would be 3 to 2. There are 3 ways that would be considered unfavorable outcomes. That would be the 3 white marbles we could draw, and there's 2 favorable outcomes. That would be the 2 red marbles that we could draw. What if we had a spinner that was divided into 3 equal parts? One's blue, one's red, one's yellow. If we were looking for probability, we might say that the probability of spinning this spinner and having it land on red is 1/3. There's 3 possible outcomes that are equally likely, and of those 3 outcomes, 1 is red. If we want to know the odds in favor of red, we would be comparing the number of favorable outcomes, which in this case is the 1 red place on the spinner, to the number of unfavorable outcomes, which is getting the blue or the yellow. The odds against spinning a red would be 2 to 1, because there are 2 ways to get something that's unfavorable, that would be the yellow and the blue, and 1 way to get something that's favorable, which is the red. So what if I tell you that the probability that it will rain tomorrow is 25%, and I want to know the odds in favor of rain? So we're going to take that 25% probability and really break it down. If the probability that we have rain is 25%, 25% is 25 hundredths, which simplifies to 1/4, then we can say that the probability of it raining is 1/4. Now what that means is that we would expect 1 rainy day out of every 4 total days. Now for odds, we have to look at what's favorable and what's unfavorable. So in this case, since I'm looking for odds in favor of rain, I'm going to look at rain as being favorable and not rain as being unfavorable. So if I expect one rainy day out of 4 total days, that means I would expect 1 rainy day and 3 non-rainy days. So I need to break it down this way so I can look at the number of favorable outcomes versus the number of unfavorable outcomes. So the odds in favor of rain are 1 to 3. I expect 1 rainy day for every 3 non-rainy days. Now you'll often see odds in sporting events. So we're going to look at the Kentucky Derby in 1973 when Secretariat, who won the Triple Crown that year, won the Kentucky Derby. His odds in favor of winning that race were 3 to 2. So what was the probability that he won the Derby? So if the odds in favor of his winning are 3 to 2, that means we would expect 3 wins for every 2 non-wins. So 3 is a favorable outcome, 2 is the number of unfavorable outcomes. So if we expect 3 wins and 2 losses every time he races, or every 5 times he races, then we would expect 3 wins out of every 5 total races. Now probability is a comparison of the number of wins versus the number of total in the sample space, which in this case is total races. So the probability of winning is 3/5. Now another place we see probabilities come up in games is something called expected value. Expected value is the average winnings over the long run when a game is played. So let's say we have a game that involves spinning this spinner, and when we spin the spinner we're going to be able to win some money. So first let's look at the spinner and determine the probabilities of spinning each of the colors on the spinner. So the probabilities are related to the area of each of the colors. So we have about half of the spinner that looks like light blue, 1/4 is red, 1/8 is dark blue, and 1/8 is yellow. And if I tell you that if you spin the spinner and you land on the light blue, you're going to win $4. If you land on the red, you can win $12. If you land on the dark blue, you can win $16, and if you land on the yellow, you can win $8. So expected value of this spinner would be, in the long run, how much money do we expect to win? So half the time we expect to win $4, an eighth of the time we expect to win $8, another eighth of the time we expect to win $16, and 1/4 of the time we expect to win $12. So to find the expected value, we need to find the sum of all these products of the probability of each event happening times the value of that particular event. So the expected value for this game is 8, which means in the long run, if we play this game over and over and over again, we expect to win on average $8 per spin. Now what if this is maybe a carnival game and you have to play to win? Is it a fair game for you if you're charged $10 for each spin? And the answer to that is no, because in the long run, you expect to win $8 per spin. If you're going to be charged $10 for a spin, that means what you're being charged is more than the average value per spin. So that is not a fair game to you. Now let's look at another game that you might have seen on TV. It's called Deal or No Deal. In Deal or No Deal, there are 26 briefcases that each contain some amount of money between 1 cent and $1 million. And your job as a player is to select a case And that becomes your case throughout the game. Um, and then you eliminate some cases as the game goes on. And each time you eliminate some cases, the banker offers you some money to stop the game and leave with that amount of money. So the question becomes, how long should you stay in the game to try to win as much money as you can? So it really is a game of expected value. And we're going to play an abbreviated version of it with only 3 cases that have $1, $100, and $1,000 in them. So we're going to start the game by picking a case. So we can pick any of the 3 cases. This is our case to play with. And let's say we decide we're going to pick case C. Now we don't know how much is in case C. It could be the dollar, it could be the $100, it could be the $1,000. The banker is going to make us an offer for our case, and we have to decide whether it's a good offer or not. So let's find the expected value for this game. We've got 3 cases. We could pick any one of the 3 with equal probability. So 1/3 of the time we could have picked the dollar case, 1/3 of the time our case could have been the $100 case, and 1/3 of the time it could have been the $1,000 case, which means the expected value of the game at this point is $367. So what if the banker offers you $350 to leave the game? Should you take his offer? And the answer is no, because that's less than the expected value. What if he offers you $375? Should you take his offer? And the answer is yes. Even though it's possible that the $1,000 case is the one you've chosen, if he offers you more than the expected value, you should leave the game. But let's say we don't leave the game. We have to pick another case to eliminate. So we either have to pick case A or case B to eliminate. And let's suppose we say we're going to eliminate case B. Oh no, that was the $1,000 case. So that means we either have the dollar case or the $100 case. So what's the expected value of the game now? Well, we've got 2 cases left. So the probability that our case is the $100 case is 1/2, and the probability that it is the $1 case is 1/2. So the expected value of the game at this point has dropped to $50.50. Not so good. Should you take the banker's deal, take his money, and leave the game if he offers you $45? And the answer is no, that's less than the expected value. How about if he offers you $55? You should take the money and run. So let's decide, which case do we want to keep? Now at this point, the game allows us to either keep the case we started with, which was case C, or we could take case A, decide to switch our cases. Let's say we're just not real confident about case C, and we'd say, let's take case A instead. Oh no, we only want $1. So expected value is something that will tell you about the average value that you expect in the game. It certainly isn't a predictor of what any one particular case in this case has in this game. So we have one more topic to talk about, and that's something called conditional probability. So sometimes the sample space of an experiment changes because of some information that we know about the experiment. And when that sample space changes because of that additional information, the probability of any event that happens after we know the additional information is called conditional probability. So let's take a look at a probability problem we've seen many, many times. If a coin is tossed twice, what is the probability that both tosses show tails? So we know that we could organize this information lots of different ways. I'm just going to draw a tree for you to look at the possible outcomes on the first and second coin. We know that there are 4 possible outcomes in the sample space that are equally likely, and if we want to know the probability that both tosses are tails, that means there's 1 out of the 4 outcomes that have tail tail, so the probability that both tosses are tails is 1/4. Now that's pretty typical of the type of problem we've been looking at so far. So let's change this problem just a little bit to see how knowing additional information changes the probabilities. So what if we say, if a coin is tossed twice, what is the probability that both tosses show tails, given that the first coin showed tails? So the additional information we now know is that the first coin, after we tossed it, we know that it was already a tail. So how does that affect what we know? Well, in essence, what we're saying is if the first coin was a tail, it's as if this top part of the tree never happened. And all we really have is the bottom part of the tree. So we don't really have 4 equally likely outcomes. We only have 2 equally likely outcomes. And we want to know the probability that both tosses showed tails, which means we only have 1 out of 2 equally likely outcomes now. So the conditional probability is 1/2. Now the tree is a very visual way of seeing conditional probability. You can also find conditional probability with a formula. If A and B are events in a sample space, then the conditional probability that event B occurs, given that event A has already occurred, is, and you'll notice the notation on the left side, that means the probability of B given A is equal to the probability of A intersect B divided by the probability of A. And to see how this formula works, we're going to look at this same problem that we just found that conditional probability for. If a coin is tossed twice, what's the probability that both tosses show tails, given that the first coin showed tails? So we're going to take a look at this very same problem. We know that the conditional probability is 1/2. But let's look at using this formula to find that conditional probability. What we're looking for is the probability that both coins showed tails, given that the first one showed a tail. Now, according to this formula, that is the probability that both coins show tails, and that's the intersection, and the first is a tail, divided by the probability that the first coin showed a tail. Now to find these probabilities, we can look at the tree to determine the probability in the numerator and the probability in the denominator. Now in the numerator, we're looking for the probability that both are tails and the first is a tail, which only happens if both coins are tails. So that probability is 1/4. In the denominator of the fraction, we're looking for the probability that the first coin is a tail, and that happens in 2 of the 4 possible outcomes. So we have 1/4 divided by 1/2, which is 1/4 times 2/1, which is 2/4, and there's our 1/2 that we got just by looking at the tree and eliminating part of the tree. So the formula is useful. You may find that if you can draw some sort of picture for the experiment or list outcomes, you might be able to find conditional probabilities just as easily that way as you can with this formula. So let's take a look at a problem with a spinner. If this spinner is spun twice, find the probability that both spins are blue, given that the first spin was blue. Now if we take a look at a tree diagram and look at the possible outcomes, we know the first spin could be red, blue, or yellow, and the second spin does not depend on the first spin, so it could be red, blue, or yellow, which means we have 9 possible outcomes in this experiment. So, we want to know the probability that both spins are blue given that the first spin is a blue. So if the first spin was a blue, that means there's two parts of this tree that could not have happened. We could not have gotten a red the first time. We could not have gotten a yellow the first time, which means we really only have three possible outcomes. And of those three possible outcomes, only one has two blues. So the conditional probability that both spins are blue, given the first spin is blue, is 1/3. So that's the end of our discussion of probabilities and conditional probabilities and odds and expected value. You'll get a chance to try some of this out in class and see what you understand.